Okay, chapter 17 and 18 are last chapters for the semester. It's exciting.
Yay!
But chapter 17 is chemical equilibrium, and then when we get into 18, that'll be acids and bases.
Okay.
So chapter 17, 1, that first section deals with the state of dynamic balance, which really just means this deals with chemical equilibrium.
I was going to say, those were some big words.
They are. But chemical equilibrium is described by an equilibrium constant expression. We'll get to what that is. And it relates the concentrations of reactants to the products.
So we're talking molarities.
Yes.
All right.
Whenever we talk concentrations, most of the time we're going to deal with molarities.
Alrighty.
Like last chapter.
Yeah.
Now, most reactions do not result in a complete conversion of reactants to products. So it doesn't react 100%. And the reactions stop because the reaction is actually reversible. So that means the products will then start to form the reactants again, and it will kind of stop the forward reaction from happening. So the forward reaction is, like the picture shows you, is your reactants going to your products, but the reverse reaction is going to be products going to your reactants. So it actually is going to reach equilibrium when those two
get in between and balance each other out.
Yes.
Okay.
So chemical equilibrium, another way to say it, is a state in which the forward and reverse reactions balance each other because they take place at equal rates. So here's just a couple examples. It's showing you nitrogen gas and hydrogen gas, and the forward reaction is equal to the backward reaction. Or they're occurring at the same rates. They're not necessarily the same amounts of reactants versus products. It just means that the rates are the same.
Okay.
Let's talk about the dynamic nature of equilibrium. This is when reactions are at equilibrium. Again, the concentrations of the products and the reactants are not necessarily equal. Normally, they're like, I don't know, hundredths of a difference, and I don't know, they're really different. Look at this guy on the escalator. You can also think about someone canoeing upstream.
Ugh.
If the water is flowing downstream and you are going upstream and you're going at the same rate that it's coming down, you're going to look over the shore and you're not going to move. Well, that's the same as this guy on the escalator. If you're running up an escalator that's going down, if you're running at the same rates, you're going to stay in the same spot.
Okay.
Now, to kind of show you that the concentrations don't have to be the same, think about a bridge. Think about, let's say if you're going from, I don't know, New Jersey to New York City, and there's 10,000 cars on the New Jersey side, and there's 50,000 cars on the New York side. It could still be in equilibrium as long as you have 500 cars traveling from New York to New Jersey and New Jersey to New York.
Okay. Because you're putting the same in that you're taking out.
Okay. So at this point, it would be in equilibrium, even though they have different concentrations on both sides.
I understand that.
Okay?
So reversible reaction also has your arrows going in both directions.
Yes.
Okay.
Yes, and that is one of your questions. What does the arrow look like? Let's see if we've got it. Another one right here. See this equation down here, the arrow that they look like little half arrows? That's what your arrow is going to look like for number 3 on your notes. Now, the law of chemical equilibrium states that at any given temperature, a chemical system might reach a state in which a particular ratio of reactant product concentrations has a constant value.
Okay.
That's a lot of words.
Yeah.
It's just comparing your reactants and your product concentrations.
All right.
But here's your general equation. So in your notes, it says write the general chemical equation. The small letters, the lowercase letters, those represent coefficients. And the uppercase letters, those represent your reactants and your products. So when we write out our equilibrium constant, that would be K, and then it has a small EQ, which I'll add that as I'm talking, maybe, if I'm that good. Where is it?
All right, so
Whatever.
as we talk about this then, we've got our KEQ equation. This is going to be your equilibrium equation. So what you can't read in there because it looks like this little squiggly.
My pen's not working, so.
It's not. Oh. Hello.
So anyways, it should be a K with a small subscript that says EQ, meaning equilibrium. I told you, it's not working.
That.
And
Why?
on the top, you're going to have the molar concentration of your products and they are raised to the power of whatever the coefficient was.
All right, so if it was 2, and let's pretend our C value was 2H2.
Okay?
So a coefficient of a 2 with our hydrogen.
Yes.
So whatever the concentration of hydrogen is from the problem, that would go in place of the big C.
So say you had a 1 molar concentration, that's what you would put in that bracket. And say you had 2 of them, okay, you're going to have 1 to the second.
Okay.
So
So coefficients
really
just are now exponents,
Mhm.
and the concentration, when they tell you what it is, you plug it in. If they don't give you any concentrations, they just want you to set up what this is going to look like. Making sure you understand where the elements need to go, make sure you put them in brackets, and making sure your products are always over your reactants.
Yeah, and for the most part, at this level, you won't have to calculate it. You just need to set up the proper equation. So what we are going to be looking for is, do you have the exponents and do you have the correct chemicals in your brackets?
Yeah, not
Okay.
too bad.
That's section 1. Let's go on to section 2. This is, again, dealing with the equilibrium constant. So if you had no idea what we're talking about, what the KEQ means, that's it. At the top, it's the equilibrium constant. It's the numerical value of the ratio of product concentrations to reactant concentrations. So again, the exact same thing we just talked about. Each concentration is raised to the power equal to its coefficient in the balanced equation. So if you have an equilibrium constant that is greater than 1, so say we're giving you a value and we ask you which ones are favored, reactants or products. If it's greater than 1, it means your products are favored. And that makes sense mathematically because your products are on top. They're in the
Okay.
numerator.
So we are going to lean towards the product end, having maybe more product than reactants.
Yes, so
Okay.
it's going to go towards the right in your chemical equation because your products are going to be on the right.
Okay.
Now, if KEQ is less than 1, then that means your reactants are favored. And remember, your reactants are in the denominator, so if there's more, then it will be less than 1.
Yep.
That was still 17.1. This is 17.2, and this is factors affecting chemical equilibrium. So we're going to talk about some French guy named Le Chatelier, and he has this principle. Sometimes reactions produce, that should say 2 with 2 rows, too low of concentrations of products to be useful. So sometimes you might want to change the equilibrium position, meaning you put stressors on the environment so you can increase the amount of product, or maybe you want to increase the amount of reactant. But think about a treadmill. Look at this girl, she's really working hard. But if you increase the speed, you have to run faster to restore your equilibrium.
Right.
If you do not speed up, then you go flying off the back because you are not going to be in equilibrium.
Okay.
Or you have to like jump off to the side.
Yeah.
Ever had to do that?
Yes.
Yeah, me too. Okay.
Don't make me go faster.
So Le Chatelier's principle basically states if a stress is applied to a system at equilibrium, this system shifts in the direction that relieves the stress. So it wants to get back to equilibrium by shifting either to the left towards the reactants or to the right towards the products because it wants to get rid of that stress.
Okay.
So you can do this in 3 ways, and we'll talk about each one in detail, or sort of. But you can change the concentrations,
Okay.
you can change the volume or the pressure,
Okay.
and you can change the temperature.
All right. So all things we've been talking about:
Yeah.
pressure, volume, temperature, and concentration.
Okay, so changing concentration. So
Okay.
you're either going to add or remove products or reactants, and that will put a stress on the system. So in your notes, you have the little bullets. Adding reactants is the first one. And this is going to increase the number of collisions between the reactants, which we learned from last chapter, increases the rate of the reaction.
Yep.
So the rate of your forward reaction from your reactants to products is going to increase, and it increases the amount of products that you're going to create. Okay, so in your notes, make sure that you have, if you add reactants, you're going to increase the amount of products. Now, number 2 here says removing products. If you remove a product, then now all of a sudden you've got this like big gaping hole on the product side. So your reactants are going to produce more products so that it can go back into equilibrium.
Okay.
And then if you add products, this is the one that's going to shift it in the reverse direction. So if you add products, then you're going to increase the amount of reactants that are made.
Makes sense.
Okay? Now let's talk about volume and pressure.
Okay.
If you decrease the volume, let's say I have a gas. If you decrease the volume, so that second picture there,
Yep.
you're going to increase your pressure.
Yep.
And if you increase your volume, you're going to decrease the pressure.
Yep.
So if you increase your pressure, you could trigger more product to be made because it's going to relieve the pressure within there. Now, the one thing that is kind of confusing, this only works if the number of moles for your reactants in your products is different.
Oh,
It
interesting.
says that in the book. If
Okay.
they're the same, if you have the same number of moles on your reactant and your product side,
Mhm.
increasing, decreasing the volume, or changing the pressure isn't going to change anything.
Just because you have the same quantity in there already.
Yes.
Okay.
Okay. So, if you increase pressure, you're going to increase the products. If you decrease pressure, you're probably going to decrease your product.
Okay.
Change in temperature. Now we've got exothermic and endothermic. So we'll talk
Ooh,
about
again.
exothermic first. So exothermic heat is exiting the system. So think of it as a product.
Okay.
Okay, that's why we have a little sun thing there for heat and light in our equation. If you increase the temperature, then you're going to basically be adding heat to the product side, and it's going to reverse the reaction.
Okay.
So you're going to increase the reactants. Now, if you decrease the temperature,
Okay.
then you're going to go towards the side that needs more heat. So you're going to increase the products.
All right.
Okay, so you just have to think of heat as a product in this instance. And if you increase the heat, you're going to go in the opposite direction. If you decrease it, you're going to go towards the heat. Endothermic reactions. Now you have heat as a reactant. So in this one, we don't have a pretty sun, but we do have a big word, heat. If you increase the temperature, you're going to increase the products. So it's kind of the same thing.
Yeah.
And then if you decrease the temperature, then you're going to increase the
Okay.
reactants. Okay? So that is Le Chatelier's principle. Remember, changes in temperature, change in pressure, and volume, but they're related. And then you've also got your changes in concentration.
All right.
And that is it for chapter 17.
Excellent. Yay.